This robot balances itself. No remote, no tricks, just physics and code. In the next 5 minutes, I'll break down how it works, how I built it, and how you can build one too. Our robot is an inverted pendulum. That means it's naturally unstable. It requires constant control to keep the wheels under the center of mass. We use an MPU 6050 sensor to measure both acceleration and angular velocity. A basic sensor fusion algorithm combines that data to estimate the robot's tilt angle with reasonable stability. That tilt estimate is sent to the microcontroller, which calculates how far the robot is from upright. Then comes the control logic. We use a PID algorithm to decide how much power the motors need to apply to correct the tilt. P, or proportional, reacts to how far the robot is leaning. I, or integral, accounts for accumulated error over time, helping correct slow drift. D, or derivative, controls motor speed. Faster tilt means faster, more aggressive motor response. This feedback loop runs dozens of times per second. The result? A robot that doesn't just react. It anticipates, stabilizes, and recovers from disturbances. Let's move on to the hardware. At first glance, it looks simple. A microcontroller, a sensor, a motor, and a couple of OLED displays. But under the hood, it's a bit more complicated. The OLEDs use I2C, and since they have a high frame rate, use lots of bandwidth. When I tried running the MPU 6050 on the same bus, things got congested. Random freezes, delayed readings, and occasional data corruption. So I split the buses. The OLEDs stay on the default I2C pins, and the MPU 6050 gets its own dedicated bus using alternate GPIOs. This keeps sensor readings fast and clean, which is critical for balance. We use an L298N motor driver to power the motors from a dedicated supply. That way, they don't pull current directly from the ESP32, which could damage the board and still leave the motors underpowered. All of this is wired up to an ESP32, which handles sensor fusion, PID control, and motor commands in real time. It's a tight loop, and every microsecond counts. For the frame, I went with a stacked shelf design. It's simple, modular, and easy to print. Just a few flat plates with standoffs between them. The top shelf holds the motor driver and OLEDs. The middle one supports the main logic board, and the bottom shelf anchors the battery. There's a well-thought-out reason for this layout, which we'll get to in a minute. Wherever possible, I use screws instead of glue. It makes components easier to swap out and gives a stronger mechanical bond. I printed everything in PLA with 20% infill. Nothing fancy, just functional, lightweight, and easy to tweak if I need to make changes later. Assembly was straightforward. First, I screwed the battery into the bottom plate. Then I add the motors to the bottom board by screwing them into the printed bridges. No glue, just solid mechanical fit. Next came the logic board. I used a piece of perf board to build a basic PCB with the ESP32, tilt sensor, and power regulator. I exposed pin headers for easy connection to the OLEDs and motor driver, which sit on the top layer. The top shelf holds the motor driver and both OLEDs. Wires from the OLEDs and driver route cleanly through a cable hole down to the logic board. Motor wires run all the way up to the driver, keeping everything modular and easy to debug. Let's get back to the layout. Most self-balancing robots put the battery up top to increase rotational inertia. It makes them harder to tip. But in my testing, that backfired. Once the robot started falling, the small gear motors couldn't generate enough torque to recover. So I placed the battery at the bottom, lowering the center of mass and making balance easier to maintain. Now finally, we will go over the code. First, we include required libraries, initialize the OLEDs, and launch RoboEyes, a free and open-source library for robot eye animations. Start the MPU 6050 on a second I2C bus. Display a boot splash screen to allow time for upright positioning. Then apply the complementary filter, run PID Control, and execute motor logic. We hit upload, tune the PID ratios, and dial in the balance. That's self-balancing robots in 5 minutes. Pretty cool, right? Surely worth a like. And if you learned something, hit subscribe so you won't miss what's next. Now let's have a look at what we've made. Balancing a robot sounds simple in theory. Just keep it upright, right? But in practice, it's brutal. Every tiny error compounds. Every misstep sends it crashing. Break after break. Fix after fix. Fall after fall. I spent days tuning the PID loop, chasing stability that always felt just out of reach. Most builds never get there. They wobble, they twitch, they give up. But I didn't let it defeat me. And when it finally stood, just for a moment, it felt like everything clicked. It's not perfect. It never will be. But it reacts, recovers, and holds its own. And for something I built from literally nothing, that's pretty satisfying.